5.3 Lesson 1 Formal Definition of Antiderivative and Indefinite Integral. Our objectives are 1. You will learn the notation used to represent an antiderivative of a function. This is also called an indefinite integral. 2. You will be able to use integration by substitution to find antiderivatives of functions. Consider the question, what is the function whose derivative is cosine? We know the answer. That function is sine, because the derivative of sine is cosine. The answer to the question is called an antiderivative of cosine, the function whose derivative is cosine. And how do we represent an antiderivative? We use the notation called an indefinite integral to represent an antiderivative. So here's how we represent this question using mathematical notation. We write that as the indefinite integral of cosine x with respect to x. And the function whose derivative is cosine is sine. Of course, you could have sine plus any constant, such as 5 or 3 or 7 or negative 1/2, etc. Because when you differentiate sine, you get cosine, and when you differentiate any constant, you get 0. So how do we read this notation verbally? We're going to read this as the indefinite integral of cosine x with respect to x. What do we mean by the integrand? The integrand is the function inside the integral sign. In our example, the integrand is cosine x. And of course, this here is the integral sign. It's an operator, which means it's telling you to do something. So it's telling you to find an antiderivative of cosine x with respect to x. An indefinite integral of f of x dx is a function whose derivative is the integrand. So for example, we have the indefinite integral of cosine x dx, and that would be sine x plus some constant of integration, because the derivative would give you, the derivative of sine x plus some constant of integration would give you the integrand. Here we have a list of some basic integration rules that correspond to differentiation rules that we've learned. We just looked at this particular one. The indefinite integral of cosine x dx is sine x plus some constant of integration. That's another vocabulary term. This c is called a constant of integration. And the reason why we need the constant of integration is because an antiderivative of the function cosine could be sine x plus any constant of integration, such as 5, 7, negative 1/2, etc. Because when you take the derivative of sine x, you get cosine x, and when you take the derivative of any constant, you just get 0. So you actually have not one particular function that's an antiderivative, but you have a family of functions that are antiderivatives of cosine. And members of the family differ by the value of the constant of integration that each of them would have. So when you're finding an antiderivative, you need to include a constant of integration, as you see in all of these basic integration rules, to indicate that you not only have a single function that's an antiderivative, but you have a family of antiderivatives, each member of the family differing by the value of the constant of integration. Make the observation that these basic integration rules correspond to differentiation rules that we learned earlier. For example, we learned earlier that the derivative of sine is cosine. So the indefinite integral of cosine would be sine plus the constant of integration, and that's what we just saw. And you can see other examples here. Earlier we learned that the derivative of tangent is secant squared. So when you have the indefinite integral of secant squared, your antiderivative would be tangent plus a constant of integration. We've learned that the derivative of secant is secant tangent. So when you have the indefinite integral of secant tangent, the antiderivative would be secant plus a constant of integration. Now we will take a look at these three here. They also correspond to basic integration rules that we've learned. However, you'll notice that we learned earlier that the derivative of cosine is negative sine. So when you have the indefinite integral of positive sine, the antiderivative would be negative cosine plus a constant of integration. Because the derivative of cosine is negative sine, so if you have negative cosine, the derivative of negative cosine would be positive sine. So you'll see the same thing with the other two that we want to look at next. We learned before that the derivative of cotangent is negative cosecant squared. So when you have the indefinite integral of positive cosecant squared, your antiderivative would be not cotangent, but the opposite of cotangent. Because if you just have cotangent, the derivative of cotangent will give you negative cosecant squared, but your integrand is positive cosecant squared, so your antiderivative needs to be negative cotangent. And of course, you can see the same thing at the very bottom. We learned before that the derivative of cosecant is negative cosecant cotangent. So when you have the indefinite integral of positive cosecant cotangent, the antiderivative would be not cosecant, but the opposite of cosecant, so that when you take the derivative here, along with the constant of integration, you'll get the integrand. And at the very top we have, of course, the power rule for integration, and we know how to use that. The derivative with respect to x of, for example, x to the 9th is simply 9 times x to the 8th. So there is a corresponding integration rule called the power rule for integration. And let's see how that works. So suppose we have the following. Suppose we have the indefinite integral of 9x to the 8th dx. How do you find an antiderivative? First of all, you can notice that 9 is a constant, and there is a property of indefinite integrals that will allow you to write the 9 outside of the integral. And once you have this, here's all you need to do. With the power rule for differentiation, you take the exponent, bring it to the front, and subtract 1 from the exponent. So the reverse of that would be when you have integration, you look at the exponent. In differentiation, we subtracted 1, so in integration, we will add 1. So when we add 1, we get x to the ninth. In differentiation, the first thing that we did was we brought the exponent to the front and multiplied by the exponent. So in integration, the second thing that we do is we will take the new exponent after adding 1 and divide by it, plus c. And you'll see that the 9 that we had factored out earlier will cancel with the 9 in the denominator, giving us x to the ninth plus a constant of integration for our family of antiderivatives. So this tells us that if you were to take the derivative of 9x to the ninth plus some constant of integration, you will get 9 times x to the eighth. This is called the power rule for integration. It works as long as the power in the integrand is not equal to -1. If it were equal to -1, we would have a different integration rule that we will learn later. Here is another example for using the power rule for integration. Suppose you have the indefinite integral of x to the seventh dx. So all you need to do is to find the antiderivative, you're going to add 1 to the exponent and divide by the new exponent. So you're going to have x to the eighth divided by 8 plus a constant of integration. How can you check to see that this is correct? You can take the derivative of what you have here, and when you do that, you will see that you get the integrand x to the seventh. We want to take a look at one more basic integration rule, and here we have the derivative with respect to x. This is the differentiation rule that we've known for a while now. If you have the natural exponential e to the function and you differentiate it, the derivative is also e to the x. And because of that, if you have the indefinite integral of e to the x with respect to x, the antiderivative will also be e to the x plus a constant of integration. Here we're looking at two properties of indefinite integrals. We've already used this one, the integral of a constant times a function. If f is a function that can be integrated and k is a constant, then you can factor out the constant from the integrand and write it outside of the indefinite integral. And we saw that with one of our examples earlier. You also have a second property here, integral of a sum of two functions. If f and g are functions that can be integrated, then the indefinite integral of a sum of two functions that can be integrated with respect to x can be rewritten as a sum of two indefinite integrals. Using the second property, I may rewrite this example as the indefinite integral of x squared with respect to x plus the indefinite integral of cosine x with respect to x. And of course, we know how to find the antiderivative for each one. Here we use the power rule for integration. Add 1 to the exponent and divide by the new exponent. And the antiderivative of cosine is sine. And don't forget to add the constant of integration. You could also apply this property mentally and just go straight from this line to the antiderivative that we had found earlier, recognizing that the antiderivative of the first term would be x cubed over 3, and the antiderivative of the second term would be sine x. And you have your constant of integration. So we've taken care of objective 1. You will learn the notation used to represent an antiderivative of a function. This is also called an indefinite integral, and we've seen some basic integration rules and examples. Now, you could have some integration problems where the integrand is perhaps a composition of functions, a bit more complicated. So how do you deal with that? You use a technique called integration by substitution. You will be able to use integration by substitution to find antiderivatives of functions that are composite functions. And let's look at some examples for objective 2. The instructions are find the indefinite integral using integration by substitution, and here's our first example. Number 1, we have the indefinite integral of sine of x to the 5th power times cosine x dx. And when you look at the integrand, you do see that you have a composition of two functions here. And whenever you see a composition of two functions, you may be able to use integration by substitution. What's the idea with integration by substitution? The idea is this. You want to see if you can rewrite the integrand in terms of another variable so that it could be made to fit a basic integration rule that we've learned about. And then you can integrate, and then you can go back to your original variable. So let me demonstrate how this is done. So you look at the composite function sine of x raised to the 5th power, and the inside function is sine, the outside function is raising to the 5th power. So you're going to do what we call a u-substitution. You will let u be equal to the inside function sine x. Yesterday we learned about differentials, and the next part of step 1 is you write then the differential of u is equal to, yesterday we learned that you find the differential by finding the derivative of the function and multiplying by the differential of the inside function, in this case dx. So the derivative of sine is cosine. You have cosine x dx. So that's the differential of u is the derivative of sine multiplied by the differential of the inside function x. So this is our substitution step. How do you know if this works out? It works out if you get something here for the differential of u that matches a part of the integrand from our original problem, because this will now allow you to do the second step. It is called the change of variables step. So in doing the change of variables, you refer to your u-substitution, and you're going to replace sine x with u because we let u be equal to sine x. So now sine x from the original integrand will be replaced with u. So I have u to the 5th, and cosine x dx can be replaced with du. So this is our change of variables step. What have we accomplished? We accomplished simplifying our original problem into a form that we can easily integrate by using one of the basic integration rules that we learned about, specifically the power rule for integration in this particular case. So now we go on to step 3. We will integrate with respect to u. So using the power rule for integration, we add 1 to the exponent and divide by the new exponent plus constant of integration. And finally, step 4 is to go back to your original variable of integration. And all you have to do that is remember step 1, you let u be equal to sine x. So all you have to do now is replace u from the work in step 3 with sine x, and we will have sine to the 6th power of x over 6 plus c. That is our antiderivative for the integrand sine to the 5th power of x times cosine x. And if you'd like to verify, you can take the derivative of sine to the 6th power of x over 6 plus c, and let's do that for this particular problem. So we may check our work by taking the derivative with respect to x of our antiderivative. So you're going to use the chain rule because you have a composition of two functions. You have sine to the 6th power of x. So the outside function is raising to the 6th power. So begin by taking, but don't forget also that you have 6 in the denominator, which you can write as 1/6. So now take the derivative of sine to the 6th power of x using the chain rule. So you take the derivative of the outside function evaluated at the inside function and multiply by the derivative with respect to x of the inside function. And the derivative of the constant of integration c is 0. The derivative of sine x is, of course, cosine x. And 1/6 times 6 is 1. So when we do the check, we do in fact see that when we take the derivative of the antiderivative, what we get is the integrand that we had to begin with, telling us that we have found the correct antiderivative. This technique is called integration by substitution, and we'll look at some additional examples. Now we look at our second example. We have the indefinite integral of x times e to the x squared. And when you look at this, you should recognize that what you have here is a composition of two functions, where the outside function is the natural exponential function and the inside function is x squared. And of course, when you look at the integrand, it doesn't fit one of the basic integration rules that we've learned about. However, you may notice that the inside function in our composition is x squared. The derivative of x squared is 2x, and we do have an x here. So that allows us to do the following u-substitution. We're going to let u be equal to the inside function x squared. As we learned yesterday, we will now find the differential of u du, which is going to be, you take the derivative of x squared, which is 2x, and multiply by the differential dx. Now, in our original problem, we don't have 2x dx, but we do have 1x dx. The only difference is the constant 2, and I can deal with that simply by looking at this equation here and dividing both sides of the equation by 2. So that gives me 1/2 du is equal to x dx. And now I'm able to use the u-substitution that we just did to change variables, to go from integration with respect to x to integration with respect to u, and when we do that, we will have an integrand that we know how to integrate. So we can replace the x dx with 1/2 du. So I can write 1/2 du. And then e to the x squared can be replaced with e to the u, because our integration, our u substitution is let u be equal to x squared. So I have e to the x squared becomes e to the u. And of course, you can factor out the 1/2, and this is something that we know how to integrate. An antiderivative of e to the u is e to the u. An antiderivative of e to the u with respect to u is e to the u. So I just have 1/2 times e to the u plus the constant of integration. We want to go back to the original variable of integration. So all we have to do is go back to step 1. What is u? U is x squared, so I write 1/2 e to the x squared plus c. And we can check our work when we take the derivative with respect to x of 1/2 e to the x squared plus c. What do we get? So you have the constant 1/2, and to take the derivative of e to the x squared, you have to use the chain rule because you have a composition of two functions. The outside function is e to the x, so you find the derivative of the outside function evaluated at the inside function, and then multiply by the derivative with respect to x of the inside function, and the derivative of the constant is just 0, so we don't need to worry about that. But what is this derivative? The derivative of x squared is 2x. And you can see that the 1/2 will cancel with the 2, leaving us x times e to the x squared. And of course, that is the integrand that we began with, showing us that this is, in fact, the correct family of antiderivatives. Now we will take a look at our third example. And our third example is the indefinite integral of x times sine of x squared dx. And when you look at this, you should see that sine of x squared dx is a composition of two functions, where the inside function is x squared and the outside function is sine. But as far as doing integration by substitution goes, you should see that if you let u be equal to x squared, the differential of u will be 2x dx. And although we don't have 2x dx, we do have x dx, and we can easily deal with the constant 2 as we saw in number 2. So now our u substitution will be, and it'll be let u be equal to x squared. Then the differential of u will be 2x dx. And we have x dx, so we would like to multiply both sides of that equation by 1/2. So we have 1/2 du is equal to x dx. So now we use our u substitution to do our change of variables step. We can replace x dx with 1/2 du. And we can replace sine of x squared with sine of u. We can factor out 1/2. And this is our indefinite integral after we perform the change of variables step. And this is something we know how to integrate easily. So what's an antiderivative of sine? Negative cosine. So we have negative 1/2 times cosine of u plus c. The derivative of cosine will give us negative sine. So if we want positive sine, our antiderivative has to be negative cosine. The last step, step 4, is to go back to the original variable of integration, and all you need to do now is replace u with x squared. So you have 1/2 times cosine of x squared plus c. And if you like to do a check, you can do that. You can take the derivative with respect to x of negative 1/2 cosine of x squared plus c. And when you do that, you will get x times sine of x squared. And I will leave it to you to do the check on your own, but you should see that. We look at number 4 now. We have the indefinite integral of 4 times e to the 5x dx. Some integration by substitution problems are easy enough that with practice you can do them mentally. This would fall into that category, but since we're just learning today, we would like to write the steps down. So we do see that we have a composition of two functions. Right here, the inside function is 5x. So we're going to do this u-substitution. Let u be equal to 5x. Then the differential of u will be the derivative of 5x with respect to x is 5 dx. So now if you look at the original problem, we have 4 dx. So how do we deal with that? So let me write our original problem as follows. We can factor out the 4 out of the integral, and we will have 4 times e to the 5x dx. So all we have to do is take care of the dx. And we can do that by taking this equation and multiplying both sides of the equation by 1/5. So we have 1/5 du is equal to dx. So now when we do the change of variables, we're going to work with what we have here, and we write 4 outside, and then within the integral we can replace dx with 1/5 du. And e to the 5x will become e to the u. The 1/5 is a constant, so we can factor it out, and it becomes 4 times 1/5 outside, or 4 over 5, times the indefinite integral of e to the u du. This is easy to integrate. The antiderivative is just e to the u multiplied by the constant 4/5 plus constant of integration c. And finally, step 4, go back to the original variable of integration simply by replacing u with 5x. And I will leave it to you to do the check. But when you do the check, here's what you should find. The derivative with respect to x of 4/5 times e to the 5x plus c should give you the original integrand 4 times e to the 5x, showing you that we have found the correct antiderivative. We look at number 5 now. We have the indefinite integral of 3 times sine of 5x dx. And when you look at this, you do see that you have a composition of two functions here. There is that constant of 3, and as we saw with number 4, it is best to just factor out that constant. And we're going to let u be equal to the inside function in the composition. Now we find the differential of u, du. The derivative of 5x with respect to x is 5, multiplied by the differential of x. What we see here is dx, so we'd like to isolate for dx here by multiplying both sides of the equation by 1/5. And with this, we're able to take a look at what we have here and change variables. So we can write 3 times the indefinite integral of we can replace dx with 1/5 du. So I write 1/5 here, and I'll write du back here. And then sine of 5x becomes, using our u substitution, it'll become sine of u. And of course, we can factor out the 1/5. So we have 3 times 1/5 will become 3/5. So what do we do now? Now we have an indefinite integral that is easy to integrate. So we will integrate that with respect to u. What is the function whose derivative is sine? The derivative of cosine is negative sine, so the function must be negative cosine. So I can write the negative in front of the constant, and this is our antiderivative with respect to u. Our next step is to go back to the original variable of integration. We do that simply by replacing u with 5x. And if you were to do the check, this is what you would see. The derivative with respect to x of negative 3/5 times cosine of 5x plus c is in fact the original integrand, showing you that we have found the correct antiderivative. And our last example for today is number 6. We have the indefinite integral of 4x plus 5 to the 7th dx. And again, this is the type of problem that you could do mentally when you have enough experience. But since we're just learning today, we'd like to go ahead and write down the u substitution. What you observe is that the integrand is a composition of two functions, with the inside function being 4x plus 5. So we will let u be equal to 4x plus 5. Then the differential of u will be the derivative of 4x plus 5 with respect to x is 4. Multiply that by dx. Now you see that you have dx in the original integral, and we can isolate for dx here in this equation by multiplying both sides of the equation by 1/4. This will now allow us to do our change of variables step. We can replace dx with 1/4 du, and the integrand 4x plus 5 can be replaced with u, so we have u to the 7th. And you can, of course, factor out the 1/4. And what you can do to find this indefinite integral is use the power rule for integration. This is step 3. All you need to do is add 1 to the exponent, so 7 plus 1 is 8, and divide by the new exponent, plus c. And of course, you can multiply 1/4 times u to the 8th over 8 to give you 1 over 32 times u to the 8th plus c. And now we go back to our original variable of integration, and we get 1 over 32. U is 4x plus 5, and we're going to raise that to the 8th power plus our constant of integration. And if you want to do the check, you can take the derivative with respect to x of 1 over 32 times 4x plus 5 to the 8th power plus c, and when you do the check, you will see that what you get is in fact, 4x plus 5 to the 7th power. So today we learned two objectives, and we looked at some examples for the second objective. We looked at several examples for how to do integration by substitution to find antiderivatives of functions.